Hello, good evening everyone. Welcome back to the live interactive session on circular dichroism and Mossbauer spectroscopy. So this is our 12th interactive session. So far we have discussed circular dichroism and Mossbauer spectroscopy. So today we will be talking about mixed valenced iron complexes, their classifications, and a few questions on the properties of Mossbauer spectroscopy. Some of the examples where we have studied about quadrupolar splitting, isomer shift, etc. So we have covered all the topics. In both the topics, circular dichroism and Mossbauer spectroscopy. And today is the last session for this. And tomorrow there is an extra session from 6 to 8 p.m. where we will be revising on whatever topics we have discussed. So if you want to discuss any doubts or you want to discuss any topic with me, please try to join tomorrow's session because that is going to be the last session of this course, last doubt solving session. So I hope you have been following the recorded sessions and notes of this. For your exam preparation or anything, if you want to ask any questions, you can write in the discussion forum or you can email me on my email address tanukaushik29 at gmail.com. So we will start in 2 more minutes, and we will be solving some questions today. And before that, I'll be discussing this topic, which we call mixed valence complexes. So we will be talking about the classification of mixed valence complexes and how Mossbauer spectroscopy is helpful in differentiating such type of complexes. Okay, so let's get started with our today's session. So first is mixed valence complexes. So this has been these mixed valence complexes are kind of classified into three different categories, and we call it Robin Day classification of mixed valence complexes. So it is a system for categorizing mixed valence compounds based on the degree of electronic interaction between metal centers in different oxidation states. Class 1 is fully localized the redox sites behave independently, essentially no electronic coupling happens in these complexes, and therefore no intervalence charge transfer band is visible. So we can say, if we talk about mixed valence iron complexes, so Fe2 and Fe3 ions remain fully localized, and these are distinguishable valence states. So if I draw uh, the Mossbauer spectra, Fe2 plus and Fe3 plus bands remains distinguishable. Class 2 is partially delocalized or valence trapped complexes. So in these, moderate coupling can be seen and hence there is an intravalence charge transfer band which is usually broad or solvent dependent. But redox centers are still distinguishable, and many molecular mixed valence compounds fall under this category. So your Fe2, Fe3 remains in a equilibrium such that they interchange, but these Fe2 Fe3 bands pair are still distinguishable. Third is class 3, which is fully delocalized. In these complexes, strong coupling is observed. The odd electron is delocalized. The two metal sites are spectroscopically indistinguishable. And in these, IVCT bands are present but have different character. That is narrower, often solvent dependent, And electrochemistry often shows a single average redox wave. In these, Fe to Fe3 are coupled so strongly that remain they appear as Fe 2.5, observed in Fe 2.5 oxidation state. So we will take an example of such complexes, and we talked about how the spectras are often solvent dependent. So we'll talk about Mossbauer spectroscopy and how the spectra can be recorded and it is solvent dependent. So if we have a Fe, so this is the example where the total charge distribution is. So we have CH3COOH, which is in equilibrium with its acetic acid, which is in equilibrium with its ionic form, and it's a bidentate ligand that is coordinating with its two oxygen atoms. And the total charge distribution on complex 6 acetates plus 1 oxo, the total charge is minus 8, and it kind of breaks down into 2 Fe. The charge on 2 Fe is 3 plus 1 Fe has a charge of plus 2. So two of the F iron atoms are in plus 3 oxidation state and one is in plus 2 oxidation state. So the overall charge on the iron atoms are plus 8, which is balancing the ligand charge. So overall the system is neutral. So now the question is how the Mossbauer spectra appears differently in different solvents for this particular molecule. How the Mossbauer spectra appears differently in different solvents. So we take one solvent which is benzene and another solvent is CH3 CCl3 methyl chloroform. So if we draw the spectra for this, So this is at 120 Kelvin, 180 Kelvin, 240 Kelvin, and this is 2 is to 1 on 298 Kelvin. Similarly, this is at 80 Kelvin, this is at 120 Kelvin, 240 Kelvin, and 298 Kelvin. So the difference in the two solvents, the spectral difference in two solvents is, in the benzene we see localized Fe2 plus Fe3 plus Mossbauer peaks at all the temperature. But in case of methyl chloroform, at higher temperature, uh, the Fe2 plus Fe3 plus peaks get delocalized. That is, the peaks get delocalized and they merge into each other. So we see localized Fe2 plus and Fe3 plus peaks at all temperature in benzene solvent, but in methyl chloroform we see at higher temperature peaks get delocalized. So here we get uh, two localized signals for Fe2 plus and Fe3 plus, but in methyl chloroform at high temperature Fe2 plus and Fe3 plus peaks are delocalized and indistinguishable. So, what is the reason behind this? In CH3, Cl3, so it is an isolated molecule that is no interaction between one molecule to other is possible. Therefore, random motion is there, which leads to delocalization and Fe 2.5 is observed. Whereas in benzene, in lattice vibration are possible. Benzene has a pi electron cloud and it stacks with the pyridine of of complex through pi stacking. Hence, intermolecular interactions are possible. That makes the molecule less dynamic. That is, the movement is now restricted. However, uh, therefore, iron cannot move, hence localized and distinguishable. So now coming up to second example, Fe So this is the second example, second complex. And if we draw a spectra for this, so this is at 5 Kelvin, 80 Kelvin, 298, and this is at 353 Kelvin. So here we get a delocalized spectra, where this one is for Fe2 plus. So let's discuss what exactly is happening in this complex. So we have first Fe3 low spin D5 complex, and the electron filling happens, that is pairing of electrons in the T2G orbitals. And in the second case, when you have Fe2 low spin, that is D6, you have 6 electrons paired in your T2G orbital. This is your symmetrical filling of electrons, and this is asymmetrical filling of electrons. So why we are talking about low spin iron complexes? The sulfur atom bound to cobalt becomes highly charged. Therefore, iron remains low spin. So, for the first case, what is possible when your Fe3 is in low spin D5 state? First thing you have to check is valence contribution. Since it is asymmetrically filled, valence contribution is non-zero, that because of asymmetrical electron filling. Lattice contribution is already there because of two different ligand environments. So since there are both valence contribution and lattice contribution are present, there is large electric field gradient in your Fe3 low spin complex. And when you have the second case, when you have Fe2 low spin, so Fe2 low spin, first if you check the valence contribution, it is going to be 0 because of symmetrical electron filling. As you can see here, that electrons are symmetrically filled in T2G orbitals. So valence contribution is 0. What about lattice contribution? Since in the complex there are two ligand environments, that is, it is bound to this but ligand scaffold, and here with the sulfur atoms, so the ligand environment is different. So there is non-zero lattice contribution. So you can say there is electric field gradient present in the system because of lattice contribution, but it is comparatively lesser than your Fe3 low spin. So how this intervalence charge transfer is happening in this particular structure? So we have iron atom, and if you draw its d orbitals, then you have sulfur, cobalt, again sulfur, So these are the orbitals, and how the electron transfer is happening. Fe2 to sulfur, sulfur to cobalt, which has a vacant or d orbital, then to the sulfur, and finally to the iron atom. Okay. So basically, intra valence charge transfer is happening through sulfur and cobalt atoms between these two iron atoms, making Fe2.5. The intermediate oxidation state. So this Fe will be in 2.5 oxidation state, cobalt 3, low spin, easy orbitals are vacant, and this Fe is also. So from Fe3 to Fe 2.5 it is going, and it is going from Fe2 to Fe 2.5. Sorry. And only on heating, this interaction, on heating only, this electronic interaction happens and exchange, or you can say intravalence charge transfer takes place. There is another example, example 3, FeS cluster to Fe2S. So the one example is ferredoxin. Ferredoxin. It is we call this electron transfer protein. So this is how its structure looks. It is bound to S16. So in its oxidized form, ferredoxin exists as Fe3. Both the iron atoms are in Fe3 oxidation state, and in reduced form, one of them reduces to Fe2. So here the isomer shift is 0.27, The quadrupolar splitting is zero point 0.6. So Fe3 is D5, high spin, and here the isomer shift is, there are two isomer shifts here. For Fe3 it is 0.35, for Fe2 it is 0.67, and the quadrupolar splitting is zero point 0.6 and 2.7. Fe2 again, high spin. So here it is asymmetrically filled. So there is valence contribution, and you have non-zero electric field gradient. So the spectra you get, this is for Fe3 plus, this is Fe2 plus, this is Fe3 plus. For oxidized foam you get only two peaks. So in ferredoxin, if two S-cysteine moieties are substituted by two N-histidines, it would be called risky protein. And how do you represent it? Fe, this is FeS4 and this is FeS2N2. and the isomer shifts would be 0.2, 4, 0.624 FeS4, 0.32 and 0.91 for FeS2N2. For reduced form, that is Fe3, Fe2, delta EQ, so you will have 0.31, 0.74 isomer shift. So you can see now that how with changes of valence contribution and lattice contribution, electric field gradients are changing. So this is where you can see that even in the spectroscopic analysis of bioinorganic structures such as these clusters, ferredoxins, uh, protein structures, etc. You can use Mossbauer spectroscopy to differentiate what is the ligand environment, what kind of cluster is like from the unknown samples. You can also kind of identify which cluster must be present in that sample. The next examples are of 4Fe, 4 sulfur cluster. This is your 4Fe 4S cluster, which has two possibilities. So the first possibility is non-favorable electronic interaction. That is, your delta G is positive. So for this, for conversion from its oxidized to reduced state, you will require minus 415 to 218 millivolt of extra energy versus SHG. So in oxidized form and in reduced form, so you have four clusters, out of which two are in three, two of them are in two oxidation state, and in reduced one, one is in three, and all other three are in two oxidation state. So we can say the overall charge balance is plus 10 minus 8 minus 4 is equal to minus 2. So the overall charge Fe4S4 is minus 2 or minus 3. Here it is plus 9 minus 8 minus 4 equal to minus 3. So overall it is going to be in minus 2 or minus 3. That is more negative charge, and delta G is positive. The second example is high potential FPS proteins, where you require plus 90 to plus 460 millivolt of extra energy for conversion, and the example is high IP. In the oxidized state, it is present in 3 3 2. The overall charge is minus 1. In reduced state, it is present in Fe4 S4 minus 2, and this conversion is more favorable. So these were the examples that we had to discuss before moving to the questions. So now, based on the discussion so far, on mixed valence complexes and our discussion on uh, isomer shift, quadrupolar splitting, etc. We will be solving a few questions from the assignment. The first question is uh, class 2 complexes of mixed valence biferrocin possesses. Option A is completely localized charges on metal centers, delocalized but distinguishable charges on metal centers, C is indistinguishable charges on metal centers, and D is all of the above. So, as in the beginning we discussed about this, how do you differentiate between the first, second, and third class? So, class 2 is partially delocalized. There is electronic interaction between the two metal centers. So, the electron is not strictly localized, but the centers remain distinguishable. And spectroscopically, this often gives intervalence charge transfer bands of intermediate width and intensity. So your right option would be delocalized but distinguishable. We have discussed about it, and I'm writing the explanation also. Class 2 is partially delocalized. There is electronic coupling between the two metal centers. So the electron is not strictly localized, but the center remains distinguishable. So this is the first question. Moving to the second question, which statements are correct regarding FeH2O6 plus? So FeH2O6 plus means your Fe is in plus 2 oxidation state. Your H2O is a weak field ligand. So the complex remains in Fe2 plus high spin complex. This is a high spin complex. So your electron filling would be in T2G orbitals and EZ orbitals. So Fe2 plus is D6, 1, 2, 3, 4, 5, 6. So your electron filling is asymmetrical. So you can say that you have a valence contribution which is non-zero. So your valence contribution is present since your ligand is same, all the ligands are same, your lattice contribution is 0. So the right options would be lattice contribution, no lattice contribution. Option C, correct, no lattice contribution, and valence contribution is non-zero. So option B and C are correct options. Next is which one is an incorrect statement regarding FeCP2? So you have your FeCP2, F is in plus 2 oxidation state. Which one is an incorrect statement? Uh, it is orange in color. So ferrocins are typically ferrocin FeCP2 are typically orange in color. So this is correct option. It can act as an electron transfer reagent. Yes. In fact, in electrochemistry, we take ferrocin as a redox active molecule to get to kind of calibrate the positions of to calibrate the scales. So it is a redox mediator. It is known as ferrocin 2. B is dissolved in aqueous solvents. So ferrocins are generally insoluble in water. Insoluble in water. Use an internal control for monitoring applied potentials. So yes, this option is correct as we discussed. Because of its uh, redox mediation, it is known as a one electron redox couple, and it is often used for calibrating the applied potentials versus SHE, RHE, etc. So it acts as an internal standard for monitoring applied potentials. The next question is, which of the following configurations will show valence contributions? So as we know, the asymmetrical electronic configurations will have an non-zero electric field gradient. Asymmetrical field orbitals will have valence contribution non-zero, and it will ensure electric field gradient is non-zero, and you will see a quadrupolar splitting. So your T2G6 EG0 is symmetrical valence electronic configuration. So it will not show valence contribution. Then T2G3 EG1 is asymmetrical electronic contribution. So it will have non-zero valence contribution. That is, it it will show valence contribution. Then you have T2G6 EG2. Again, it is symmetrical. So valence contribution would be 0. Then you have T2G3 EG2. This is also Also, symmetrical contribution, electronic configuration. So valence contribution would be 0. So option B is correct. So for valence contribution, you should have a symmetrical electron filling. So the gist is valence contributions to the electric field gradient arise when the metal's d electron distribution is non-spherical or anisotropic. Okay. The next question is the point group of the most stable configuration of ferrocene molecule is. So ferrocene can exist in ferrocene can adopt two conformations. First is eclipsed conformation and staggered conformation. So in eclipsed, you will get this kind of configuration. In staggered, you will get this kind of. This has a D5H point. This belongs to D5H point group, and this belongs to D5D point group. In the last session, we discussed about this, how to find out the point group of ferrocene. So we also solved these two conformations. And for your information, experimental and computational studies show the staggered D5D form is lower energy, that is more stable conformation. The eclipsed D5H is a local maximum or high energy conformation. So your D5D conformation is the most stable conformation of ferrocene molecule. So in this plot, you have been given the Mossbauer spectra of iron phenanthroline isocyanide metal complex. You have been asked these questions. Figure A represents Figure A represents the Mossbauer spectra of uh, as we discussed in the examples today, typical Mossbauer spectra, signatures depends on oxidation state, spin state, and temperature which basically affects the relaxation and population of spin states. So if you see, while going from up to down, there is a decrease in isomer shift. This is high isomer shift, and we know high spin Fe2 complexes gives larger isomer shifts relative to Fe3 or low spin Fe2 complexes. Uh, because of greater s electron shielding difference and more electron density differences at the nucleus. High spin Fe2 gives larger isomer shift because of s electron shielding difference and more s electron density difference at the nucleus. It can also show broader or magnetically relaxed features at high temperature. So your right option should be high temperature Fe2 high spin state complexes. The next question is, figure B represents the Mossbauer spectra of. So figure B is basically at a lower isomer shift. So we can say it is Fe, either it is low spin state Fe2 or it is Fe3. So the option should be op- low temperature Fe2, low spin state. So your low spin Fe2 is often diamagnetic in strong fields and gives a sharp doublet with a relatively small isomer shift and small quadrupolar splitting. So you can see that there is a very small quadrupole splitting as compared to this. And about temperature, at low temperature, magnetic relaxation effects are frozen and a clean low spin doublet is observed. So this is your Fe2 low spin. Next question is, in a D2H point group, the number of C2 present is. So for this, if you take a good example of D2H point group, for example, ethylene, diborane, or naphthalene. So let's take the example of ethylene. C double bond C H H. So you have to find out how many C2 X's are present. So there is one passing through this C double bond C. Then there is another coming diagonally outside. And another is this. So basically, in a D2H point group, There is one principal C2 axis and two secondary C2 axis. Do it. So the right option would be option 3. So these were the assignment questions. So there are I'm giving you some other mock questions that you can solve later. We have discussed all these topics today, so I hope you can now solve these questions. The intervalence charge transfer IVCT band is characteristic of A. Class 1 mixed valence systems, B. Class 2 mixed valence systems, Class 3 mixed valence systems, or D. None of the above. Question 2. An Fe2 high spin complex shows a larger isomer shift than Fe2 low spin complex because option A is S electron density at Fe nucleus is higher in high spin complex. B is S electron density at Fe nucleus is lower in high spin complex. C is Fe ligand bond length is shorter in high spin complex. क्लास चल रही है मैं करती हूँ फोन. Question 3 is, at lower temperature, the quadrupole splitting delta E Q in Fe two complexes usually A increases, decreases, remains constant, or changes sign. Question 4. Which statement best explains the stability of ferrocene? A. Strong sigma bonding only. B. Pi back bonding between Fe and Cp minus rings. Cp bonding provides delocalized pi electron overlap with Fe d orbitals, or ionic bonding between Fe2 plus and Cp minus. Question 5. Which of the following contributes both to both lattice and valence terms in electric field gradient? A. FeH2O 6 2 plus. B. FeCN6 4 minus. CONH3 CH3 plus. Question 6. Which of the following species has D3H symmetry? A. BF3, B. NH3, C. XeF4, and D is SF6. Question 7. Which configuration shows no valence contribution to the quadrupole splitting? A is T2G6 EG0, B is T2G3 EG1, C is T2G3 EG2, and D is T2G6 EG2. So this is about today's session. We have discussed about mixed valence complexes. We discussed in detail some of the examples and the application of Mossbauer spectroscopy in identifying mixed valence complexes in clusters, iron sulfur clusters in proteins, etc. So, and also solving questions, and I have given you some of the mock questions to solve also. So this is the end of the Mossbauer spectroscopy whole topic. I think we have covered all of the topics in details. In these sessions, I have given a brief summary of each of the topic, and we solved some questions on every topic. So I hope things are clear to you by now. In the next session, tomorrow's session, which is from 6 to 8 p.m. Tomorrow is an extra session. So I would request you to join in the tomorrow's session if you have missed on understanding any of the topic, if you have any doubts with any particular topic. So the tomorrow's session is going to be the last one. So if you are following these recorded lectures, please try to attend tomorrow's session, and I'll try to summarize all of the topics, and if possible, we'll be solving a few questions also. So I hope things are clear to you. Uh, so I'm going to end the session now. Thank you for your attention.